Hello everyone. This is my paper review project. I would like to share with you what I have reviewed. Um, this basically have to be with half a gray satellite or overestimate groundwater depletion in Northwest India aquifer. It was published in 2016 in the Scientific Report of Nature. This article reviews remote sensing application using data from GRACE satellite to monitor changes in total water storage, including all forms of retention of the precious liquid both on the surface and on the ground, and the benefit to society of having tools that provide regional coverage of the current capabilities of groundwater reservoirs, um, and which can be determined in advance the status of reserve in different aquifers. The current work reviews the impact of Northwest India aquifer, specifying the approaches made by previous work that provide a holistic assessment on the groundwater stress and resilience over aquifers. However, the author notes the existence of uncertainties in groundwater storage depletion, and this is the source of this analysis presented here to assess in detail the depletion of Northwest India aquifer. Processing GRACE data requires noise reduction at high frequencies using low-pass filtering. The data suffer a signal loss from filtering, which need to be restored using a few different techniques. The authors were aware that the last version of spherical harmonic solution of the Earth gravity field from GRACE further reduce uncertainties in total water storage, changed by up to 40%. So they considered examining groundwater depletion rates using the latest uh, the latest spherical harmonic solution and different approaches for the same region and period of time in Northwest India aquifer, and evaluating groundwater depletion estimate with groundwater-based monitoring data, uh, which are imperative to develop through understanding of uncertainties in restored groundwater depletion rates from different approaches and how much groundwater has really been depleted in Northwest India aquifer. The starting hypothesis is that the spatial distribution of water storage change for a study region may impact the utility of both unconstrained and constrained forward modeling. The integration of the spatial pattern of water storage change, it may significantly improve delineation of exact spatial pattern of groundwater depletion from GRACE satellites. The methodology they use started by testing the impact of the distribution of groundwater storage change on unconstrained and constrained forward modeling to recover signal loss due low-pass filtering using synthetic data. integrated spatial pattern of groundwater depletion from global hydrologic modeling to estimate groundwater depletion from GRACE and ancillary data from 3 state regions on Northwest India aquifer. Compare GRACE basic approach uh, for estimating groundwater depletion for the 3 state region and compare GRACE derived groundwater depletion with ground-based monitoring data. We're using 3 state region like Punjab, Haryana, Delhi, and Rajasthan for a total area of 438,296 square kilometers in Northwest India aquifer. The result obtained in this research was the groundwater depletion rate from groundwater level data for the 6-year period, and a specific yield for 3 state region was estimated to be 2.8 centimeter. Groundwater depletion shown in negative. That is for the graphic that I will show you next. Variation in groundwater level for most of 20 selected sites across the 3 states showed rapidly declining trend, particularly in the east, but much less in the west, with even some recovery of groundwater levels in the west. Specific yield values to compare groundwater levels changes to storage for unconfined aquifer for Punjab and Haryana were estimated to be 0.1538, which is dominated by sandy alluvium, specifically yield 0.15 that account for 98% over 2 states. The specific yield in Rajasthan was estimated to be 0.1, which is dominantly by sandy alluvium, 60%, and sandstone, 11%, with a lower specific yield of 0.045. Here we have some graphics, the map of Northwest India aquifer. In the left corner, we have the 3 state region, Punjab, Haryana, and Delhi, and Rajasthan in India, shown by the blue polygon. Those areas are irrigated. They are equipped with irrigation. The areas equipped with irrigation with groundwater from Aquastat data of the Food and Agriculture Organization of the United Nations. This is shown here in the big graphic, okay? And the slope variation in groundwater levels. See, those scale represent the slope in the groundwater level. And in that left lower corner, we have the groundwater level monitoring data over the 3 state regions and in surrounding areas for a period of 3 years. The open circles in Z represent the 20 selected groundwater monitoring sites. Those circles are very small over here. So basically, what we can see now, the data provided by the satellites of GRACE have been filtered, have been processed statistically, and now compare with the data coming from the ground. In the feature 2, we can appreciate a full presentation of the groundwater depletion rate from PCR globe from the period of 2003 and 2010. They are synthetically distributed in A. Forward modeled groundwater depletion rate distribution after 500 iteration using unconstrained forward modeling. Okay, over here, much better, is much better represented. And in the lower left, which is C, it is the forward model of groundwater depletion rate distribution after 500 iteration using constrained forward modeling. And at the right lower corner, which is D, the filtered groundwater depletion rate from A and C after low pass filtering. So the filtering basically filter the data, eliminating the noise. In the feature tree, we have a tree graphic with the series. They are the rate of groundwater depletion from original Grace TWS, which is total water storage is the word. Total water store changes without filtering minus GLDS as a surface storage. So those we change in the period of 2003 to 2010. Okay, this is the A right here. B is the rate of from filtering Grace GWD rates and globally constrained forward modeling. And C is the rate for GWDA time series and original surface changes for SSMS. I forgot what mean changes from GLDSAs. So far, so they are the pair in the graphic, the previous graphic that we saw in the previous slide, and the time series. So in the X we have the years, and in the Y we have the groundwater storage anomalies, water storage anomalies, and SMS anomalies. Okay, in this slide we present the discussion of the outstanding result. They actually have a lot more of result, but I just synthesize what I consider the most outstanding. And they are the estimate of groundwater depletion from constrained forward modeling for the three-state region during the 5 years period is 2.5 with error of 0.01 centimeter centimeter per 8, which is less than the previous estimate of 4 mass minus 1. The surrounding areas of the three-state region exhibit appreciable groundwater depletion. In addition, the estimate of groundwater depletion rate, 3.1, and the surrounding areas is significantly higher than in previous work. This is change, the work of change. The constrained forward modeling based in groundwater depletion rate from the same period is a study of 2.1 mass minus 0.1 centimeter. The three-state region, which is consistent with what Chen et al. 0.21 obtained using unconstrained forward modeling. The groundwater estimate using constrained forward modeling make grace estimate more meaningful by incorporating a priori information on groundwater-based irrigation. And that's it. This is the end. I choose this paper, even though it's pretty complicated for my level of understanding, because I'm amazed that we can work now with remote sensing for monitoring groundwater. Thank you very much for your attention.